I don't even know the name of it. Oh, that's fine.
So just to give you a heads up, this will record for at most 20 minutes.
Okay.
How long is your presentation going to be?
I'm scheduled for 1 hour. It might be less.
Okay, so what I'd like to do ideally is try to break this up into 3 or 4 segments.
Okay.
As I get close, I'll probably do like a little jig here just to let you know that I'm going to stop and then restart.
Okay. Sounds good. Check, 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 check. This is turned on, I think.
Yeah.
All right. Good. Do you want to do a brief intro?
I'm scheduled for 1 hour. It might be less.
Yeah, this is the YouTube stream.
All right.
It sounds okay to me. The screen looks a little blurry, but that may be the wine from last night. I don't know.
That's interesting that it is a little blurry still.
We're all a little blurry. It's early. It's Saturday morning. What are you going to do?
So go for it.
Introduce yourself.
Okay. My name is Franklin Amador. I am an electrical engineer. My degree was both electrical and electronics. So that's why I'm here, because I could do both, dabble in both. This project has been a long time coming. I apologize for not presenting back in February, March. That's when it should have been. But I've been traveling quite a bit for work internationally. Let's see. I got a Green Erase Development Board 2 years ago. I sat on it for a year. I just couldn't wrap my head around it. I technically learned fourth on this thing because I didn't know that much. I didn't have an application or didn't do one prior to that. I tried on a previous presentation I did and got stuck halfway through because I wanted different fourth kernels talking to each other over a protocol that they could all agree to. And well, it led me to this. On this, and I developed this just to learn what would it take to get a one-wire protocol ported over, configured, running, and have data coming in. Prior to this, I had no knowledge of both the one-wire or the green arrays, and so here I am. On top of that, the end goal for me was to try to write parallel programs for genetic algorithms that can genetically evolve circuits in just about any kind of process. So before Green Arrays, I was actually reading Mark Koza's work here from Stanford. And to put genetically evolved software on parallel computers as opposed to an array of computers in a room this big was ideal for me. So that's where I was going. So here I am. It's taking a long time, but it's slow. This is just interest I have for things I think about and where it can go. Whatever I'm going to show today is posted on GitHub. It's called the GA144 one-wire application note. I had a mentor, business partner. We went back and forth on the copyright on this. Now it's free software. It's a GNU version 3. So it's there, available. You could download it. It's the PDF that you'll see here, presentation, the documentation for the PDF in Word. And yep, that's pretty much it. Okay. Oh, before I start, I read this book. It's It's from Russia. It's called Ceton. It's about a ternary fourth computer back in the 50s. Ternary? Trilogic?
Oh, I'm sorry.
Sorry,
no.
maybe it's the way I said it.
Ternary.
Ternary, yeah.
Ternary.
They had a fourth OS, three binary, three state logic back in the 50s. And it's a pretty awesome book. I recommend reading it just for historical purposes. But I think they were the first ones. Russia, 50s. Okay. Here. It's a pretty cool book. It gives you the architecture and the instructions for it. There's some overlap. I think it could be ported over to a green erase chip. Okay. So to get started, just a brief introduction. This is our F18 computers on a green erase, 144 of them. I'm using one for the one-wire kernel. One of the nodes, talking over one pin. We'll get into that later, but I thought I could do it in one node, and sure enough, I could. If I had CRC and other functionalities, I could use two nodes and leave it standalone away from the VM that they have, but I integrate it to the VM, the Polyforth virtual machine. So what I've done here is I'm using the host chip with the VM in this array and the CPUs here, coprocessors. I'm going over, let's see, yeah, from 307 up to and all the way to 516, and then 16 talks to 517 in the code. And all of these are just Snorkel and Ganglia up to here, and my code is running in the 517. I originally wanted to do it on node 600, but there's code already for some of the base stuff that the green erase people have done. And what I wanted to do is add a one-wire, like 10-bit digital output so that I could do a chip select over SPI. Because once you start playing with this and you want all these functionalities, you run out of I/O really fast. So I wanted one wire to talk to a device that could do 16-bit, 32-bit, whatever digital outputs over one wire, and then just change the bits I want for the chip select on the SPI. And it's still doable. I think after this presentation, maybe they'll do something like that at some future time. There were some other data sheets for the GA4 had a one-wire description there, but when I went to look at it, it looked like it was a different type of one-wire, like a Manchester encoded one-wire communications. So it wasn't really the Dallas semiconductor one-wire. Oh, so because I work in industrial for process control and power plants and all these things where you got to program things, I come across vendors. They say they can do all these things. Realize some don't. They're just limited in what they have, but they have to sell. So whenever I come across something, I find something that can be added or positive, I tell the vendor, I tell the people who are creating these things. So after playing with this, I gave two advices, one to Chuck, one to Green Erase. The first one was on the virtual machine with the coprocessor. This is kind of deck space over here, and then there's the SerDes right here. What I suggested is, why don't we, as you go away from the virtual machine, on these nodes right here at I/O, so that you could have the fastest I/O closer to the VM. Because the further you get away from the VM, the delay, the latency, all that drops, and then your millions instructions per second are still there, but the speed on how you do things will get delayed. So what I suggested is, okay, the two co-processors, these are open, so you could have a co-processor with SPI communication here, push the co-processors even further, put one here with SerDes, and put one here with serial, and then put one down here for something a lot less speed intensive, like a one wire. So you use the co-processors to get the data in and out really fast without having to crisscross all of this. The problem is once you start crisscrossing, you got to look at your path and not get into a loop for data passing, messaging passing. That was one suggestion. The other suggestion I had, which I emailed Chuck, was doing some research on this. Writing parallel programs has gone back for a while now, especially with the architecture. So I was reading this book from Gellinter and I forget the other guy's name, Carriero, How to Write Parallel Programs, the first course. How to Write Parallel Programs with Gellinter and Carriero. It's basically when I read this is Linda description of parallel programming. What I interpreted was this is a hardware version of Linda in some ways. Not fully, but not all the way, because in Linda you could pass data through node to node and around, but not through the nodes. And what I suggested is I found some free code called SpaceWire from Europe, and it's VHDL code. And I said, why don't you use this? It's a router for passing data back and forth. And I said, why don't you use this and use the 5th port that these things have, connect to it, and let it route around the nodes. So you don't use the processor for data.
As a way station.
Yeah.
So what you're saying is this routing, you literally can say, I want to go like from node
Here to there.
Up to 617.
And then not interfere with any node.
It'll be essentially one hop.
I don't know about that. But because it's a router at each point, so you have to route through the routers all the way up there.
Okay.
Yeah. But you could get around the nodes and let the nodes do its calculations. So again, this is me figuring out how to best improve things, and later on realized that Parallella, they're creating parallel chips, 32 bits. They have 16 and 64 nodes. They think in 4 years they're going to go up to 1,000 nodes in one chip. I have a board. I'm playing with it. It gets really hot. But adding those routers here, I think, is still valuable for this architecture, because, yeah, you might increase power consumption, but it's probably going to double. So 1.2 watts. That's not bad. So anyways, that's just improvements I'd like to give people if they're willing to listen, and resources and money will say the other part of that. Okay, so continuing on. So this was actually a couple iterations of trying to get to it to work. I bought a chip, this one, the Texas Instrument TXS 0102 for level shifting. between 3 and 1.8 volts. And it was too small. I couldn't solder anything to it. You look at the picture, it looks big, but you know, they're actually very tiny. So I had to make my own circuitry to get this thing to work. It's hodgepodge, but it works. And well, proof of concept. So as I said before, I'm using one node to send and receive bytes over the one-wire network. What I did find out was one wire is kind of a misnomer, because if you really do one wire, there's not enough power for the end device to convert the data. So you need 3 wires, power and ground. So one wire for data would be a more accurate term. I took Brad Rodriguez one-wire code. It was in machine language for another device, Camel Forth. I had emailed back and forth about the copyright on that, and he said, as long as you port it to something else that's not what I've done, then you're an original. So, but I said, okay, if you feel that way, that's great. But he still went and put a free clause on there for that code, because a lot of people are using it. So it's on GitHub. It's JPL version 3, free. Do whatever you want with it. So here's my hardware interface. I could have gotten rid of this if I would have used a MOSFET, but I used a BJT. Just because I could go back and forth and design these things, no big deal. Originally, I had done a straight wire here, and next thing I know, my finger's burning up.
So that transistor is a level shifter.
Yeah, yeah.
Okay. It's kind of hard for me to see. I see something that looks like a 1.
Oh, this is 1.8 and 5 volts. This could be 3 but 5 volts is where it is.
So he's written it using European style. It's 1V8. Okay. I wasn't even sure if that was a V or a U.
Yeah, it's a V.
Okay.
Sorry.
That's okay. That's okay.
So this is the architecture. Here's the node 517, pin 17. The code's written for 17. So if we got to move to a different pin, then you got to change one spot in the code, and it will be fine. I think the code also could be added, modified to do both master-slave. From what I read is Dallas Semiconductor doesn't like you doing slave devices because they want to sell their own. They came up with the standard, so I understand. But you can do both. So yeah, I had this. I didn't limit the current to the base, so my finger got hot. So I threw another one of these in, and it just worked. So I was happy. Just a level shifter. Okay, let's jump right into it. I'm assuming some of you know one wire, some of you don't. I'm going to go through it as if from scratch. Basically, everything's high, and the master initiates a call. And the master pulls down the line for that long, releases it after a certain amount of time, 15 or 60 microseconds. It waits to see if there's anybody there. And what they do is they pull down the line low, the slaves. So then the master knows, oh, there's somebody there. And it's all time-based. There's no clock. The clock is internal. So because of that, all you have to do is get the timing right on the GA144 core to do the timing based on this, and it talks.
So one wire protocol is a master-slave.
Yes.
Yeah. So you have one master and many slaves.
Yeah. Yes. I went through this iteration to see what it could do or what it can do. I'm starting to think you could have multiple masters and somehow share the network, but that takes more coordination.
It's kind of like I2C.
Okay. So That's what happens. This is a response from the slaves. So that's the reset. It's called a reset. And once the master does a reset, everybody shuts up and listens until it's released, and then they all respond with a hi. Okay. So how do we write a 1 and a 0 to the bus? And what the master does is it pulls it low, waits for a while, releases. And if it's if the pull down of the low is long enough, then it's a 0. If it's pulled down and released right away as a write, then it's a 1.
I mean, this is the master doing this, right?
Yes, yes. The master initiates everything, so it needs to be able to write and read. And then you'll get a response back, and I'll show you that in a second. And I'll run my simulation. You'll see the response on the bus from Logic Analyzer I have. In a read, it's the same. The master pulls down low, releases it, and then if all the slaves release, or the slave it's talking to releases it, then it's a 0. For a read from the master, it pulls the line low, releases it, but if the slave keeps it low, then it's a 0. And if the slave and the master release on a master read, there's slots for each one, then it says it's a 1. So it's a talk between, okay, it's time-based between the master and the slave. Now again, there's no clock. The clock is internal. It's just timing. You got to time it, and the master times it all. The slaves just sit and read and do their own timing based on responses from the master. If there's no response after a while, it just defaults and goes back to waiting for initialization pulse. So there's different protocols or different things you can do. This one specifically for the temperature one-wire device I have. But each device from one-wire has different hex codes that you could tell them, and they respond back with the actual data for that hex code. So you do initialization, they respond back with a reset. Then you send this code, and then you read-write to 8 bytes to get the data back. So I'll show you that in a minute. But basically, on this one, 44H converts whatever data it has over to be able to transport it out. The scratch pad is stuff you can put in there. There's registers you could load in there. You could read and write into it or copy it. I do this, but I don't do anything else with it. But you can. It's real easy now after going through this process. Oops. So this is sending transmission packet. You do the initialization reset, and then you send a command. The master will always send a 0 when it's reading from the device, and wait for the device to respond with a pull low or left high, and based on that, it starts reading the data from it. So the least significant bit goes out first, and then you get the most significant bit later. So this is the master sending these, and then the one wire slave pulls in the data.
Okay, this is just showing just a transmission.
Yes. Right. No, it's just a transmission. And it's a 33H transmission. So that's the master sending it. This is the receiving data. So you can tell the master is always sending out a high, pulls down for the timing, and then waits a response from the slave, whether it's a 1, which gets released right away, or a 0, which holds it for a period of time, and then releases.
The master will hold the line low for a certain amount of time, then go and start sampling after a certain amount of time.
Right. So it pulls down low, tells the slave, okay, I want the next bit. And then it says, well, if I release, when you release it to 1, if I hold it for a certain amount of time for that slot, then it's a 0. And the slot, I'll go back up to that. I wasn't clear enough, but here. So the master writing up there, doing its thing, and then the slaves writing back when the master reads.
So really what you do is you, as a master, you flow, or it looks like a microsecond.
Yes.
Then let it go.
Let it go. After.
I think what you would do is you would start immediately sampling, just to see what you've got over a certain amount of time. Yeah, then you can say, oh, if it's like all low, then I got 0.
So I wait this much, and then sample it after that.
Okay.
Once I do,
after 15 microseconds,
then I sample. Then it doesn't matter when do you do this. It just has to be within this much time, and then when everything gets released back up, the timing goes away.
But in this case, just to make sure, you would make multiple samples just to make sure you've got the state.
I don't on this, and it works. I know. Well, that's where CRC would come in if it. Yeah,
because you know what you're doing is you're bit banking.
Yeah, exactly.
On your toes there.
Yeah, that's a good point. I didn't think about that. But, what's that? Right. Try it 3 times, and if it's, all the same, good. That's a good point, because I had to read other documentation to see what it would be if it was a long line. Because you could go, I don't know, 250 feet, or maybe less. I don't know, but they get noise to be in the line when the longer you go. And because it's one wire, I always think it's going to be on the same board where the chip is, but that's not necessarily true.
I'm just taking a guess. If you had a long line like that, I would probably use a differential.
Oh, right. 45. Yeah.
Yeah. Common mode reject on wires.
Yeah. Then it's a 4-wire device, not a 3 or a 1.
Depends on the environment.
Yeah. But from what I see, you won't go that far with 1 wire. That's why they have the other protocols, and you pick what you want. This is good for like surface board on the same place where the chip is, where the master is. Oh, yeah, right here. Okay. So when you read the scratch pad, you actually get 8 bytes. So any kind of data read from it, most of the times you'll get 8 bytes back. And then you do what you need to do with it. The temperature is the first 2 bytes. This is just for memory. 4.5 reserved, and this is for conversion to get more resolution out of it, like 4 decimal points. So once you get the data, you got to convert it over to something that it's understandable. The least significant byte, byte 0, will give you the data, and then the most significant byte will give you if it's a negative or a positive temperature reading. So based on that, you can do the conversion, which is pretty easy. This is a table that you could see like the scaling of it and what the hex value would be.
It's half a degree Celsius.
Yeah.
That's right. Wow.
But they give you more bytes, so you could do finer resolution. But just to read those two first bytes, the byte 0 and byte 1, then you get a half resolution. Here's the equation you use to convert over to a more finer resolution if you need that. And I did a table what that would look like if you're just getting the hex value, converting to decimal, then do 5 multiplication, you get the data how you want it. Or division by 2, then you get no resolution on that, just a 10th resolution. So with the other bytes, you can actually get 4 decimal points if you want, just for that conversion. I didn't do that, but it could be added. I just read and divide by 2. Okay, so now we can get into it. So the biggest problem I had is when I started coding is what the timing is on these codes for the F18. I looked at Chuck's code, and he had a lot of 4 ... micronex for delays, and finally figured out that's about 200 of those will give you 1 microsecond, 204 micronex. So based on that, on average for that node, I don't know if they're all the same, but you do some tests and then you find out what the timing is on that. So that was the first thing, figuring out what timing was for looping through this. So after that, I was able to create the reset and the slot word to read each one or write through that. I was actually surprised, not totally surprised, but when I started this, of course, I started using their tech support, Green Erase tech support, and one of the questions was, why do you want to do this protocol on this chip? It's so freaking slow, you know. It's just me playing around, you know. So they thought it was funny that I was looking into it. Later, I realized what he meant, because to do the timing and delays, I sit here waiting 100,000 instructions that don't do anything. It's just looping for the one wire's data to come in and out. So I could be doing 100,000 different things at each slot when this thing's running. So I see what he means. I mean, see what they meant. But yeah, it's a slow protocol, extremely slow. There's a I forget what it's called. It's a shorter burst packet that you can do. Some one-wire devices provide that, and you could go 10 times the speed. And I thought about how I could structure my code on the node to be able to handle both. And the only thing I could think of was writing an algorithm that could, when I run it, it'll just change a couple of registers and come back and forth, which led me to believe, like, you could change, if you know an algorithm that could change the code on you you could switch tasks or different programs altogether just by running and changing data on the registers. You just got to know the difference between both codes that you want to run, and then somehow come with an algorithm small enough that can do that here. That was kind of interesting to think about.
So I'm about to interrupt and restart footage share.
Okay. So here's the code. This is all I have running on one node. The delay, the wait, which is about 500 microseconds, it's 100,000 instructions. I came up with one wait statement that I could use multiple times as opposed to actually giving it different wait commands. Because if it's just waiting, it doesn't have to wait different times. It's just one wait command could do quite a bit, and it worked. I'm reading the pin. That's reading what the pin is at B, and I AND it to see if it's a high or low, and then I use it in the code. Pull up high, that's 0 store to B. Pull it low, 1 down on pin 17. Okay, so the biggest words here are reset and slot. Those were the first two diagrams I showed. The master pulls low, waits a while, releases it, and waits to see if there's a slave present. That's a reset. And it'll come back and say yes or no. There is somebody there or no. So that's all reset does. The slot, what happens is you put down the line low, wait a while. I check to see after I release if the line's low. No. I pull the line low, wait a while, and check to see if after a certain time it's a 0 or 1. If it's a 0, then I go to the next, which is what the master wants to do, either send or no send. It's been a while. I haven't gone through this code, but it works. I'll show you. It was interesting going through this because I could show you iterations of I did for this code. It's like 15, 20 different versions of it. It was fun trying to compact it down because you're given what 64 words to play with. So I liked it. It was a challenge. It was kind of like building a puzzle. So just to continue, I could have done different send and receive commands, but the code down here would have been a little bit different. I didn't want to do that. So one thing I like about this structure of forth is if you don't have a semicolon to return back, the code just continues. So you could have multiple words, jump in the middle of a word, run part of the code, and then continue on. And it's exactly what I did here. The return is right there, but I could have done a return here and a return there and done the send receive at different commands, but it just goes through slot and runs all the way through. Does it one shot, whether it's reading or writing. So finally, when those two were pretty good, timing wise, I haven't had the CRC in there or the check 3 times. But I think it can be done. Just delay it a little more, check, delay it a little more, check. But here's the final words, and I said PF or polyforth. what I want Poly4 to do is come in here and look at and run these commands, not the other ones. So the kernel's up there. Here's the interface to Poly4. And again, I went through iterations. I was actually using Node 5.16 for some of the code, but in the end, I realized I just could write it all in here. And this is your reset. Once you run reset, it pulls a line low and waits to see if somebody's there. The slot, this is read-write slot for the reading or writing. And here, you do it 8 times in a loop. It's very efficient, very small code. Okay. Oh, before I even touch hardware, I use the SoftSim. Very cool, very amazing. I was blown away when I ran it because there's so many things you can do. You know, you could emulate it just about anything on there. So that's where I tested out the code. I even, with the help of Charlie, I wrote some code that would simulate random stuff in the pin with SoftSim, so I could figure out what data. I finally got data out of it, random data, but it was good data. Just testing that out. I like the fact that the code for SoftSim to add change registers or add to the stack and work with that. It's the same as the ones you use when you're plugged into the board. You know, that's cool. You don't have to relearn new words to do that, so props for them. That's good. Okay, so how do we get the code in the green arrays board and get it to load the right stuff on the node when you want to test it? I have, that's the loader. I reclaim. That's just to clear things, but I didn't have to do that. I threw it in there. This document is kind of like a hodgepodge of their app notes. Somebody here was doing code like this and documented that way. Somebody else was doing it that different. So I took whatever they had, structured it the same. So if you look at different app notes they have, it'll kind of overlap in the structure, which is what I wanted. So it also kept me from documenting something appropriate. It kept me to documenting it properly. Okay, and then one thing I finally realized is in some code I've seen from the Green Arrays guide, which I looked through a lot just to see what they had and what they're thinking. You could actually load zeros on the stack, because when you reset the stack, it's 15555, and it's a 10 10 10 10 10. And if you're moving data on the stack, those ones carry through even though there's no data. You know, there's nothing there. So if you set it to 0 and you're moving stuff back and forth, it gets to be a little more efficient code, energy-wise. You're not pushing ones that you're not using. You're just pushing nothing. So on the node itself, the A becomes a write port, the B becomes an I/O port, and that's how the code is structured. You can change that if you want, but that's how I did it. The stack is all zeros. And I believe I used that on boot up. And then where I'm going to pass data, read data from. So this thing is sitting, waiting for data from the virtual machine. Or if you put code in 5.16, it'll wait for data from 5.16. So it sits there doing nothing until you run it through, and then waits and sits there. So if the only time it's consuming data is when it's doing its for loops, which is, like I said, a lot of looping just to get the timing right. So this is the code to get SOSSIM to let you simulate, in this case, a wave on that pin. And there is a load that you have to do it at block 216 to get it to run, and then it'll just change when you're running it. But you gotta comment it out when you're actually doing field tests, because it'll load it when you don't want it on the simulation. It's documented. It's nothing fancy. It's in the user manual. So I'll let people research that. So when I test on the chip, I create a loader and a way to connect to the node if I wanted to. So load the code, connect, hook to 517, do some test with the loader. That was after I had finished the code on the node. So I wanted to see how it performed, how it was doing, if it was getting data in and out before I build the polyforth interface. So it's a lot of word testing, test. Every step is a test for me for this. It took about a month and a half. And at nights when I was carrying my son on my back because he was sleeping, and my wife was like, go to bed. It was fun. So that's what the code on 517 would look like when you do a read run. Now, when we get to the polyforth, so this is the hard part I had. I would have a question, go read the manual. Okay, go, whoa, this thing's super condensed. I have another question, go read the other manual. I have another question, go read this book. Oh my gosh, it just kept, the knowledge for this I didn't have. I had to learn it. It was a lot of reading, a lot of technical stuff that I had to read. It's very dense. A paragraph is not to be wordy or anything for them. It's actually documenting something you're going to need later. So it's very dense. So, okay, so I learned all this is the hardware stuff. I learned how to connect to it, load it, test it, all of this. And I'm like, okay, now I get to polyforth. Know nothing about it. I start reading again. There's more manuals for that. So this is definitely a steep learning curve, I have to admit, because it's not meant for like the average Arduino people who can code in C and then boom, it's running. It could be, but it is what it is. So my interest was just to see what it would take to code in it, what the limitations were, and see where I could go with it from there. Things like bit mining, that could be good for this. Okay, so here, the code I had loaded on the array forth, I loaded here on this block to run when I run polyforth. And initially I was doing 450 load to get the IDE booted, to get the code in there. And after a while, Charlie was like, why are you using that? We got a better, faster version of it. Do 430 load. And I tried it out. It took like 3 seconds. I didn't have to wait 15. So that was good. So once I load it, then I could start interfacing to it. But to interface to the node, you need the snorkel ganglia architecture they wrote, which is block 142. Again, more reading, more figuring out things. This is actually helpful for me, this one, where you can write and read from the node at the same time. I think people are using this, but later they added that. So this is for people, this block, people who don't want to code like this to get into the node. It's a very easy way, cookie cutter, that's what they need. Stuff like this that people can use right away, get in and out, turn an LED on, whatever. Something fast, quick, and simple. So I finally started when the hardware was good, everything was good on that side. How do I interface into it and get data out? So I started the code. I loaded the snorkel ganglia code, and then I started my code right at 300 up to 306. I'll show you in a minute what it looks like when I boot it up. But I didn't know how I was going to do this, but they had good examples on their app notes. So the same reset, polyforce reset word in the node is, if you didn't notice, it was address 29 for that. The gray, I'll show you in a minute. Page up. Page down. The good thing about this is you could put these words and it'll compile and let you know where that is in memory. So here's 29, 2B, and 2D. I need to know that so that I tell polyforce, go read at this register and run this word. And then if it's sending something back, read it back. So here's an interface to that. Okay, so snorkel ganglia tying into 16 because the code is on 17. And then on 16, I say read to the port, right port, which is 1D5. Read and write. And then once you get the data, do this, which is, I'm getting rid of the high byte. This is the same thing for the slot and touch. Polyforce slot, polyforce touch. Here I'm calling it one wire. 29, 2B, 2D. And again, this is because on polyforce you get 2 bytes, high and low byte, because the CPU is 18-bit. This is 16-bit, so you get some high bytes.
If it's the numbers are expressed big endian, right?
What's that?
The hexadecimal numbers are expressed as big endian.
I think so.
Yeah, that's what it looks like. So the 2029, the 20 would be the high byte, the 29 would be the low byte.
Yes.
Yeah. Okay. So one thing I didn't know I could do is send some data and then send more data and read back data, which was helpful. And then it all came together. Once I got through that, I could write the put data on the bus or get data from the bus. So we'll see here. Show me if I have one wire on the device. This was helpful because I could tell it, give me your ID, and I'm gonna read. Put that on the bus after I reset it, and tells me yes, I'm here. If a device is there, then send 33 hex, and then loop and get 8 bytes real quick after that, and then just drop it. And I want to see what's on this here on this stack. from the stack, drop it, so I could see it on the screen. And then that's helpful. Now, if you do this, you don't have the hardware. I wrote this so that it could emulate something just to see if it's talking to the node. So it worked. It's good to do that. Show ID helps because you could just put one device, get the ID of it, and create a mapping to that ID, and later on just call that and get the data out of it, which I'll show you in a minute. So ROM search algorithm, they have an algorithm on this protocol to look for the ROM ID on every device. So this algorithm coded will give you every listed device on the bus. So if you don't do the one at a time, and you have like 10 of those and you don't know which one's which, then you do this search and it'll give you the address for each single one.
So what you're saying is these one wire, it's more than just a thermometer.
Oh yeah, yeah,
TI uses it for a lot of stuff.
yeah.
Okay, because I could see this being used in a mesh network. You know, where now you get temperature, but you get humidity.
Oh yeah, yeah,
Combustion products.
right. Medical products.
Exactly.
Yeah. One thing I was thinking about that it could be applied for security on panels.
What?
Panels?
Panel?
Panels, electrical panels where there's, you know, a computer in there and, you know, substation stuff for power plant or gas and oil. And in the panel, put a device that can guard the panel with a RFID or something like that.
Right.
And, you know, unlock the panel if everything's okay with an embedded system like this, but everything being one wire. So if, you know, you could put smarts in that line, so if somebody tries to tamper with it or it's an ID that's not recognized, then give an alarm or something, or not unlock the panel if the RFID doesn't match. So anyways, this is a search algorithm. I started porting over the code from Brad Rodriguez in Polyforth for the high level stuff. The low level, it was all arrayed for. So one thing I didn't notice is I didn't see a left shift, right shift in Polyforth. So I had created my own. And if it was all negative and it was right shifting, I wanted to keep it all negative. If it was positive, right shifting or left shifting, keep it positive till it hits negative, you know. But that's what that was for. I could have done just for this next, you know, shifting. But when I do that, I tried it. Charlie suggested, why don't you condense the code and go that way? I tried it. The ROM search didn't work. It wanted these to stay this way. If it was negative and you're right shifting, stay negative. If you're left shift, then that changes. So that's why that if -1 is there.
Can I interrupt here real quick? I need to change battery.
Okay. We'll take a brief break.
You gotta converge, sort of in the next 5 or 10 minutes, get a few minutes for questions, so we can
Yeah.
head over to lunch.
I'm almost done.
All right.
How am I doing on time in?
Oh, you're awesome. It's 11:27, and nobody ever died from being 5 minutes late for lunch.
Oh, okay. Yeah, this is close to the end now. Okay, continuing on. So this is part of the ROM search. It took 3 blocks to get it in there. It would have taken more, but I wanted to condense it. Eventually, that's the heart of it. I won't get into it, but the diagram is there for people to trace out all this if-then statements, because I did. And one thing I realized when I ran it on one shot, it would give me the 2 ROM IDs from the devices. I ran it again, it would only give me 1. I ran it again, it would alternate back and forth. I just kept scratching my head. What? I threw this in there at the last. You know, if you're really done, you know, be done. Otherwise, keep going. And then I cleared it up. That was I emailed Brad, told him you got a bug in your code, and he was happy for that, but kept going. So now when I do a real ROM search, I get all the IDs, not 1 and then 2 and then 1 and 2. Oops. Okay, so once I was done with that ROM search, it's right there. I want to show IDs, and this is the code that will show you all the IDs by running that code over and over and over. Then here's the code for sending ID, read the scratch pad, convert the data in the one-wire device. That's one of the hex codes. Read temp, and then I got more conversions here, like put a decimal point, the ID. I created a sensor with this data on there, with a variable with this data, and I pass it to the ID, and it takes care of sending it byte by byte. So when I say read from this device, it goes through with that proper ID. Finally, I do, okay, on this word, select sensor 1 and convert the data for that weight this long, and then read the data and then put a decimal point. So I did that for both sensors. And then the last example is to read the data, the scratch pad data from the device, the 8 bytes that are just sitting there. So I took this out of the manual from Dallas, and this is how you would transmit and receive data based on their protocol. You send a reset, you receive the presence pulse from the slave devices, you send a 55 hex, you send the ROM ID, you send the final code of what you want it to do, and you wait, you send a reset pulse again, and you tell it to, okay, what's your data again for that? So it's well documented. What I've outlined here for that example does exactly this with few words. So when I run it, this is the bug I had. Show IDs, there would only 1 come up. Fix the bug, finally. This was the 2 IDs. I used that to create the words or the sensor array for the ROM ID. And then I do a final 1, final 2 to read the data out of it. Then I do the example to read the scratch pad. And then I read it in hex format. It works. 1 node on the GA144 and a lot of block code in the virtual machine. Any questions?
More of a comment. What's good about this is you're showing, especially for the green arrays, that you have a host interface, which is polyforge, and you have the green arrays, which is the array forge. You're showing here the communication between the two. The other one is, as you said, you asked green arrays, hey, I want to interface this one-wire device. The guy said, why? That's awful slow. Well, this is good because in certain applications you have very slow devices versus, say, doing DSP.
Right.
And the idea that the one wire is not just a thermometer, it's
It's array. Yeah.
Fancy device.
Well, it opens up green arrays market.
Yes, exactly.
Exactly. To be able to read to these devices, even though they're not producing the chips, there's people that use it. Exactly. So now there's a way of getting into it and getting data out of it.
Right. That's the thing. You really come a detailed example. tutorial.
Mm-hmm.
Just first steps of using green arrays. This is very good.
Took a while, but yeah. Again, I like it. In the end, I give props to Charlie for helping me, and his patience went a long ways. And I say this architecture is simple and modular. It is. Once you get the understanding of, the words and what words do and what they mean, and it's a lot of stuff, tools you need to get to this level, and they have it. It just takes a while to ramp up to speed to it. But for people that grew up with fourth and no fourth, this no big deal.
Not really.
Oh, okay. Yeah. So finally, this is free software. It's on GitHub. Download it. Do what you need.
I noticed you had some copyright statements. Have you? Which copyright?
The GNU version 3.
Oh, you're going to GNU?
Yeah. Well, I say what I say. It's free. So. Thank you.
Thank you.
You.
Would you be willing to give a short version of this spiel at fourth day?
Maybe. I don't know what my plans are. I want to be here, but I could be.
I want you to be. Anyway, coordinate with Charlie.
Okay.
If you can manage
Yeah.
to
Right.
maybe give us 10 minutes of this
Okay.
or whatever Charlie wants, because
Right.
since it's so GA 144, I don't want to tread on his bailiwick.
Right.
He's programming the afternoon.
Okay.
On
Cool.
behalf of GA, on behalf of Green Arrays. So
I was going to show you the example, but it's actually documented, so I might not need to do that.
you want to take a few minutes after lunch?
Yeah. Sure.
That'd be great. Thank you. John mentioned all the wonderful, various exciting one-wire devices. Besides thermometers and memory products, what are there?
Capacitive touch
Kevin
buttons.
was about to answer that, right?
No.
Oh,
Oh.
I thought you were gonna.
I can
Sure.
Google it as well as
A
the next
website-
guy.
Exactly.
Yeah.
Exactly.
I play with this one. There's others. There's memory. There's clocks. There's encryption. There's yeah. I mean, it's a lot.
Encryption, like for like logging on.
No, well, you could put a key in the chip and talk to one wire, and the encrypted key is given back to you. So, and there's memory, and then there's a whole
What
slew.
I mean is you can use that to, instead of type password in, you just have your thingy that
Yeah.
logs you in. Like a smart card.
Or the code for the green arrays can be ported into that, and then on boot up, streamed right out. And then that way you keep your stuff kind of, if it shuts down, it's gone.
All
Yeah.
the Green Arrays code could be on a flash drive type thing that you load every time you power up.
Yeah.
You don't have to have it in there.
Yeah.
So they've got a dead device whenever they look at it. But
Right.
when you come up to it, you've got it running.
It's also like USB devices. I understand where they, just like you said, they're dead devices, but you have to load firmware into it.
Yeah, yeah.
So that they,
It'd be loading the firmware, and
Yeah.
it's a little less firm than.
yes, it's like, I've worked on some classified devices. The only time they're classified is when they're powered and operating. Other than that, they're just a
Yeah.
big giant piece of silicon.
Okay.
Let's be off.
Anything else to say? We'll be back.